We begin with a specific fragment of the Fibonacci sequence, 55, 89, 233, 377, and 1597. We will use these 5 integers as the coefficient data to build 2 distinct algebraic systems. These equations show our models. Left is system C, a linear quadratic system. Right is system O, an octic quartic system. Both use the same 5 numbers. There is one structural difference. The lighter blue and heavier gold coefficients trade places between linear and octic terms. In mathematics, this specific structural swap of degree assignments is called an algebraic parity inversion. This single structural inversion acts as an absolute geometric switch. It dictates whether a system produces intangible complex bounds or generates a finite physical topology known as the Orc modality. System C is a mathematical dead end for real numbers. It contains exactly 0 real solutions. System C is constrained entirely to the complex plane. It lacks any real Cartesian coordinates, leaving it as an abstract concept with no physical footprint. System O uses the exact same numerical DNA, yet by running those numbers through the parity inversion, it produces a 32-node complex structure harboring exactly 8 real graphable branches. We will not use brute force computation to find these branches. We will analytically prove the exact algebraic mechanism that forces this topological transformation. To prove system C lacks real solutions, we first reduce it to a single variable quadratic equation. This diagram shows the process. We isolate the variable y in the linear equation and substitute that resulting expression directly into the quadratic equation below it. Clearing the denominators and combining like terms leaves us with a single unified polynomial. To understand the roots of this polynomial, we calculate its discriminant. The discriminant sign dictates whether solutions are real or complex. This calculation shows the discriminant for system C. The massive subtracted constant term forces a strictly negative result. That negative sign represents the plunge into non-real mathematical space. You cannot take the square root of a negative number using real numbers. Because the discriminant is strictly negative, the coefficients are real, and the polynomial is degree 2. The fundamental theorem of algebra forces system C into exactly 2 complex conjugate roots. We extract the imaginary components of x and y from these complex conjugate roots to observe their behavior. Plotting the roots, imaginary heights v and t form a bounding box. Applying the linear equation to these vertical components drops the real constant, leaving 55v plus 89t equals 0. Rearranging yields a precise ratio. The imaginary parts multiplied to exactly 89 over 55. System C lacks real solutions, and its imaginary boundaries are fixed by the ratio of its linear coefficients. This rigid geometric phenomenon is called complex phase conservation. We now examine system O. Directly calculating the roots of a degree 8 octic system is computationally uninformative. Applying the substitution capital X equals x to the 4th and capital Y equals y to the 4th reduces the octic equations into a manageable quadratic linear system. The parity inversion means the heavier gold coefficients, 233 and 377, now govern the linear terms. This structural shift in the linear equation redistributes the arithmetic weight. Substituting isolated y into the quadratic equation, the dominant constant term no longer forces a negative result. The newly calculated discriminant shows this reduced weight shifts the mathematical sign to strictly positive. Swapping degree assignments moves us beyond the complex plane. A positive discriminant guarantees distinct real roots exist. A strictly positive discriminant dictates that our reduced quadratic equation will produce exactly 2 real mathematical roots for x. Mapping these x values into the linear equation yields corresponding y values, establishing 2 distinct coordinate pairs. These equations show the exact algebraic values for the 2 coordinate pairs. A numerical check confirms the leading terms exceed the subtracted radicals, meaning both x and y are strictly positive. Graphed, they sit securely inside the positive upper right quadrant of the Cartesian plane. These positive real anchor points provide the foundation to reverse the substitution and map the 8th degree topology. To solve the original system O, we must mathematically reverse the initial substitution. We need to find x equals the 4th root of x and y equals the 4th root of y. Complex algebra dictates that any positive real number possesses exactly 4 distinct 4th roots in the complex plane. This diagram illustrates the lifting process. Multiplying the 4 roots for x by the 4 roots for y generates a 16-point matrix in the complex plane. With 2 distinct anchors, we double those 16 permutations. The octic system generates exactly 32 complex solutions. 32 complex solutions exist, but our objective is isolating the strictly real branches that reside within the real Cartesian plane. We apply our final constraint. While a positive real number has 4 complex fourth roots, exactly 2 of them are real, 1 positive and 1 negative. As the complex matrix fades, we isolate the real positive and negative roots for x and y. Combining them produces exactly 4 real coordinate pairs per anchor. This final graph plots all 8 real coordinates, creating a perfect 8-branch topology, the Orc modality. Of the 32 possible permutations, these 8 specific coordinates are the only branches that reside within the real Cartesian plane. This 8-branch real topology proves that parity inversion is a precise geometric bridge. By swapping degree assignments, we extract a system out of the complex void and anchor it permanently to physical reality.